In this lecture, I'm going to show you an interesting relationship between powers of a species and what are known as sequences of binomial type. So for every species R, and every non-negative integer lambda, let's write, we can look at the species R to the power lambda, which is R multiplied by itself lambda times, and look at its exponential generating series. And so that's let's say that is n greater than or equal to 0, and let's denote the nth coefficient of this power by Rn lambda. Then it's not difficult to see that these coefficients satisfy the following identity. Rn of lambda plus mu is sum k goes from 0 to n choose k r lambda k r k lambda r n minus k mu. And this is just like the binomial expansion. If you take lambda plus mu to the power n, if you define Rn of lambda equals lambda to the power n, then this identity here would just be the binomial theorem. But we are seeing here that this occurs in a more general context, and namely when these coefficients come from powers of species. Let's look at some simple examples which you may have seen before if you solved the practice problems. So the first example, let's just take R to be L. Remember, L is the species linear orders, and it is equal to 1 plus x squared and so on. So an example, if you look at an R5 structure on a set with 8 elements, can be visualized. Here's an example of such a thing. So you need to give divide the set into 5 parts which are ordered. So the first part, the second part, the third part, fourth part, and fifth part. And now you have 8 points numbered 1, 2, 3, 4, 5, 6, 7, 8. So here I've just chosen to put them in a certain way, and we need to linearly order each part. So I'll just do it like this. And 2 of these parts are empty. So these parts are numbered 1, 2, 3, 4, 5. So this is I should say an L to the power 5 structure on 8. And so you see from this picture that this is also equal to the number of ways of placing 8 flags on 5 flagpoles. You're allowed to have more than 1 flag on each pole, and the order in which the flags are placed on each flagpole is matters. So you can draw it like this: pole 1, pole 2, pole 3, pole 4, and pole 5. And my flags, on the first pole I have 2 flags, on the second pole I have no flags, on the third pole I have 4 flags, On the fourth pole I have 2 flags, and again on the fifth pole I have no flags. Let me put the numbers of these flags. And how many ways can this be done in? Well, for the first flag I had 5 choices. I could have put it in any one of the 5 flag poles. But for the second flag I have actually 6 choices, because I can put it on any of the 5 flag poles, but if I put it on the first flag pole where the first flag is, then I can either put it above or below the existing flag on that flag pole. So I get 5 into 6. And now for the third flag I have 7 choices, because firstly I can put it on any of the 5 flag poles, but there are already 2 flags and I have to decide where to place it relative to those 2 flags. Now if those 2 flags were on separate flag poles, then each of those whether to place it above or below those flags would give me an extra choice. If they were both on the same flag pole, then I have 3 places where I can put it, either above both of them, between them, or below them. In any case, I get 7 choices and so on. And so since there are 8 flags, I get 5 into 6 into 7 into 8 into 9 into 10 into 11 into 12. So in general, you can show that Rn lambda in this case is lambda into lambda plus 1 into lambda plus n minus 1, which is called the rising factorial, lambda upper n. And what you get from this lemma is that lambda plus mu upper factorial n is summation k goes from 0 to n. N choose k, lambda upper k, mu upper n minus k. Now, what about the proof of this lemma? Well, the proof of this lemma is actually very simple. You just note that R of lambda plus mu as a species is R to the power lambda into R to the power mu, and therefore R lambda plus mu x is R lambda x times R mu x. And now you just compare coefficients. And when you do that, you will find that you get exactly this identity. Okay, so let's look at another example. Let's take R to be the species 1 plus x. So it's either an empty set structure or a singleton set structure. So an R5 structure on say 4, you can't have an R5 structure on a set with more than 5 elements, because you'll have to divide the set into 5 pieces, and each piece you can have at most 1 element. So it's given, it can be visualized like this. So you have to divide the set into 5 pieces. Yes, order is important, 1, 2, 3, 4, 5, and in each piece you're allowed to have 1 element of the set 1, 2, 3, 4 or none. So here's an example of an R5 structure on 4, and this is the number of ways of placing 4 flags on 5 flagpoles with at most 1 flag on each pole. So I can describe this by the flags on poles. Picture would be something like this. I have 5 poles and I have flags on the first, the second, the third and the fifth, and the flags are numbered 2, 1, 4, 3. And if you think about this, then the number of ways of doing this. So for the first flag, this is just like the previous one, except it's even simpler. For the first flag, I have 5 choices. For the second flag, I have to put it on any of the poles except the one on which the first flag was, so I get 4. The third flag has to go on any of the poles except the poles where the first 2 flags were, so I get 3 and 2. So this is the following factorial. In general, Rn lambda is lambda into lambda minus 1 into lambda minus n plus 1. This is called the falling factorial. So it's a product of n numbers starting with lambda and decreasing by 1 each time. And what we get is the falling factorial is also a sequence of binomial type. So lambda plus mu, falling factorial n is summation k goes from 0 to n choose k, lambda falling k, mu falling n minus k. Let's look at one more very interesting example which is related to Stirling numbers of the second kind and the associated Touchard polynomials. So let's take R to be the species of partitions, set partitions. So remember that we can think of this as E of E plus. It's an assembly of non-empty set structures, and in this case what we get is Rx to the power lambda, the generating series. Well, we know that it is x of x minus 1 to the power lambda, which we can write as x of lambda into x of x minus 1, and that is just sum k goes from greater than or equal to 0 e to the x minus 1 to the power k lambda to the power k by k factorial. Now observe that e to the x minus 1 to the power k by k factorial is the generating series of ek e plus, which is the generating series of set partitions with exactly k blocks. So this sum here is equal to summation k greater than or equal to 0 power k x lambda to the power k. But this is given by Stirling numbers of the second kind. So this is summation k greater than or equal to 0, summation n greater than or equal to 0, s n k x to the n by n factorial times lambda to the power k. And so Rn lambda in this case is sum k greater than or equal to 0 s n k lambda to the power k. Of course, this k greater than or equal to 0 can be replaced by k goes from 0 to well, actually k goes from 1 to n. Well, k goes from 0 to n unless n is 0. K goes from 1 to n unless n is 0, but we can write k goes from 0 to n because a set partition of a set with size n cannot have more than n blocks. And this you can regard as a polynomial in the variable lambda, and this is called the Touchard polynomial Tn lambda. And what we get is that the Touchard polynomial is a sequence of binomial type. In other words, Tn lambda plus mu is sum k goes from 0 to n tk lambda Tn. Oh, I forgot to put in the binomial coefficient. N choose k tk lambda Tn minus k mu. This Touchard polynomial has an interesting connection with probability theory. So the Poisson random variable, a Poisson distribution with expectation lambda is given by, we say that a random variable x has is distributed with Poisson distribution with expectation lambda if probability that x is equal to k is e to the minus lambda to the k by k factorial for all k non-negative integers, and probability of any other real number occurring is 0. So this is the Poisson probability distribution, and it turns out that and I would encourage you to try to prove it, the expectation of x to the power n is Tn lambda given by the Touchard polynomial. The way you show this is that you show that the expectation of the falling factorial is just lambda to the power n, and using this and some of the things we've learned about Stirling numbers, you'll be able to deduce this identity here. And the identity that Tn lambda is of binomial type tells us, so let's call this star. So the identity star is a manifestation of the fact that if you have one random variable x that is Poisson lambda, another random variable y that is Poisson mu, and x and y are independent, then x plus y is Poisson lambda plus mu. So with that, I'll stop this discussion of sequences of binomial type. However, they do have beautiful and rich theory via umbral calculus.